So let's start off this presentation first with a little celebration, and this is my ancestor from long, long ago, Gustav Knospe. Gustav was a violin player and a professor. In fact, we come from a long line of professors all the way back to the Bronze Age. As you can tell, he was the life of the party, and so he's a good person to bring out now to have a little celebration over the difficulty of the last lecture and your overcoming it. So here's to you, dear viewer. We're now going to use these ideas, and it's going to be more downhill from here on. This lecture and the following one is going to examine averaging of signals to produce other signals. And the motivating question for this lecture is, how can signals be made simple? Or another way of phrasing it is, how can we economically describe signals? That is, describe them with less information. So consider this. A signal, such as shown in the graph here, consists of an infinite number of data points. So that's a lot of information, an infinite number. We'd like a much simpler way of describing a signal. One way we could simplify our signal description would be to take data points for certain values of time, perhaps evenly spaced values. So that's shown here with these gold dots on our graph. And this is referred to as sampling. But unfortunately, this method loses information, like all methods of trying to simplify a signal. It completely loses all the information about the signal between the sampled points. And there's one important point here to make before we move on, and that is there is less information in a simple signal. Now there are some signals where there's no information lost when we do sampling. So for example, this signal shown here, y of t, it's 20 between 0 and 1 second, 10 between 1 and 2 seconds, and 30 between 2 and 3 seconds. Now this signal can be completely described by the sequence of values 20, 10, and 30. And so this is a very simple signal being described by so few numbers. So let's bring in an orthonormal basis signal set, f1, f2, and f3. f1 is 1 between 0 and 1 second, f2 is 1 between 1 and 2 seconds, and f3 is 1 between 2 and 3 seconds. And using this basis set of signals, we can write the signal y of t in terms of the basis and coefficients. Y of t is equal to 20 f1 plus 10 f2 plus 30 f3. Now let's think about using this same idea on more complex signals. Signals with more information than the simple signal we saw on the previous page. Let's try approximating y of t, shown here in the graph, by an approximation ya of t. And so we can do this. It's very reminiscent of what we were working on in our last lecture. We have a set of orthonormal basis functions, f1, f2, f3, and we can find the coefficients, in this case 2, 8, and 5, such that we get the best approximation of signal y in terms of the basis functions. Now the coefficients that give the best approximation are the averages of the signal y over these respective intervals. So the average of signal y over 0 to 1 second is 2, the average of signal y between 1 and 2 seconds is 8, and the average of signal y between 2 and 3 seconds is 5. These coefficients are the components of the signal y in the directions of f1, f2, and f3. So this is just like we were doing in the previous lecture. We can find these coefficients by taking the circle product of f1 with y to get c1, f2 with y to get c2, and f3 with y to get c3. Now, since C1 is the average of the signal over the first second of time, the operation F1 circle y is the same as taking the average of y over this interval. We can see that easily by the definition of the circle product. It's the integral from minus infinity to infinity f1 of t, y of t dt. And since f1 is 1 between 0 and 1 and 0 otherwise, this is the integral from 0 to 1 of y of t. And that's the average of y of t. The same is true for finding C2 and C3. They are the averages over the second and third interval. So in this slide we have the general idea. Define function f of t as in the diagram shown at the bottom of the page. It is a pulse between time t1 and time t2 with a height of 1 over the duration t2 minus t1. The average of a signal between time t1 and t2 is the integral from t1 to t2 of 1 over t2 minus t1 times the signal y of tau d tau, where tau is simply the dummy variable of integration. And you can verify that that integral is equal to the circle product of f of t and y of t. So here are some important things to note about the averaging process. The average does not entirely throw away what is happening between samples. Unlike sampling. In sampling, there are certain values of data which are completely ignored in simplifying the signal. In averaging, all the data is used to determine the simplified signal. However, when we average, information is still lost. That means you cannot recover the original signal from the approximation. I'll also note that unlike sampling, the averaging method treats all points equally. In sampling, some points are very special and all their information is retained, while other points, all the information is lost. In averaging, all points are treated the same. So let's try to get a very visual notion of what the difference is between sampling and averaging. On the left, we have our good friend Gustav. This is the original painting of him. And on the right, I have a version of the painting where I've done sampling at various points. Before we get into the details of the sampling, let me just state that the painting itself is a signal. It's an ordered set of information. The ordering is done spatially and in 2 dimensions. So for the painting we actually need 2 independent variables. So how did I do the sampling? I divided the painting up into 20 squares, 4 across and 5 down. And at the center of each square, I found the color of the painting, and that came to represent the painting over that entire square, just like sampling a signal represents the signal over the entire interval. I didn't conduct the sampling in every square, so you can still see the original signal in some of the squares on the sampled side. Now let's look at the averaged version of this original painting. You'll note in certain ways this actually does capture the original better than the sampled version, though in other ways perhaps it's not quite as good. In the sampled version, the face came out to be very red because of the particular point that was at the center, while the average captures the blend of colors in the face. Over by the arm, the gray and the silver are captured better in the averaged than in the sampled version. However, by the violin, perhaps the color is not captured as well. This may not be entirely surprising. When our eyes are evaluating which image is closer to the original, they're not considering what the energy of the discrepancy between the two signals is. The evaluation is being done on the basis of entirely subjective notions of the closeness of images. Let me also note at this time that the process of averaging and the process of sampling are systems. They take one signal and then produce another. That is our definition of a system. So hopefully at the end of this lecture, you now have a better idea about averaging versus sampling of signals, and you understand how to do averaging in order to simplify a signal. In our next lecture, we'll look at a different kind of averaging, the moving average of a signal.